All right, everyone. Welcome to CPE 517-WS Digital and Computer System Architecture lecture. This is lecture 1, part 1, History of Computer Architecture. I'm your instructor, Professor Han Liu. First, some logistics. For this class, some of the slides will be adopted from the following the textbook slides and other researchers, such as from David Patterson, Sen Lipsky, Howie, and David. All the credits goes to original authors and all the errors are mine. Reordering and modifications might be applied due to our lecture requirement. Okay, so before we talk about the history of computer architecture, let's first talk about how far have we been through for computers. I know for a lot of you, you understand that computer starts probably from the World War I, right? So, but actually the first very popular one or famous one is ENIAC from United States. For that one, it occupies actually 50 by 30 foot. That is 15 by 9 meters. That's very, very large. It's literally a building, right? So this is a very famous figure we show in the middle. The ladies are trying to, run some programs by putting in some punched papers. Well, starting from there, and today we see we have a lot of computers. Okay, starting from some sensors, see here. Okay, we have this Apple Pencil. So it's a computer. And then we have some sensor network like, for example, the sound control lights or light control lights, bubbles, or those kind of things. Or it goes to multimedia player or smartphones, cameras, set-top boxes for the computer, for the television, laptops, or automobiles, or very famous recently, the driverless car, servers, routers, games, robotics, or a huge supercomputer. So we have a variety of computers in front of us today, from ENIAC, which is a huge computer before. We've been through so many things, and it's really because of the computing technology or computer technology have a lot of improvements. For example, in the performance improvements, we have improvements due to semiconductor technology, such as we have packed more transistors in the same chip, right? Like from 5 nanometer to 3 nanometer recently, this technology that gonna give us a shorter distance of communication and then have a better clock speed. Improvements in computer architecture, like we have compilers, we have CISC-RISC instruction set architecture. Those kind of things lead to performance improvements. They together have enabled light-weighted computers and productivity-based managed interpreted programming languages. Okay, so we have in the bottom layer of physics, like atoms or the silicon, these kind of things. On the bottom, we have, on the top, we have application. In between, it's clear we cannot have an application directly run on this kind of physics, right? So there's a big gap between application and physics. Okay, what are the gaps? So how do we bridge the gap, right? So there's a lot of things in between. For instance, for an application, we have algorithm. Let's use, for example, on social media as an example. Finding friend recommendation, for instance, right? So friend recommendation requires an algorithm of like a triangle counting, right? Triangle inequality. Like this. Okay, let me draw it for you guys. Okay, we have here A, nodes B and C. Then we can recommend B and C to become friends, right? So this is the algorithm that facilitate this friend recommendation application of Facebook or Twitter, etc. And then how to implement this algorithm? We have different algorithm programming languages, Java, C, C++, or Scala, those kind of emerging languages. And below that, we have the virtual machine or LLVM, those kind of large language compilers or operating system to support this kind of application to run. And below that, we translate these kind of languages into low-level instruction set architecture, like the adder, subtraction, this kind of instruction, and opcode, and then operands, etc. Below that, we have the macro architecture, like 5-stage pipeline, reservation station, cache coherence, what we're going to cover later. Translating those architecture organizations into RTL workflow of the circuits or gates, and then below is devices, and then that is physics. So we see from application, we have algorithm, program language, operating system, virtual machine or compiler, instruction set architecture, microarchitecture, register transfer layer, level, gates, circuits, devices. We have like 9 total of layers in between application and physics. So for computer architecture, in the broadest definition, it designs the abstraction of implementation layers that allow us to access information and processing applications efficiently using manufacturing technologies. So putting in another word, basically, we see computer architecture is actually an abstraction, an organization of the hardware, right? So you see instruction set architecture, macro architecture, those are concepts. Those are not real physics or electronics, right? But on top of instruction set architecture and macro architecture, they are operating system, programming languages. Those are software. So you can see on top is the software. Below instruction computer architecture is the hardware. In between is the computer architecture. Okay, this aligns with our first introductory video. We see computer architecture is not purely like circuits, electronics, like how do you design AND gate or gates. Those are gates below RTL even. But you have to understand those kind of physics or hardware designs in order to better support the upper layer software, right? So sitting in between software and hardware, this makes computer architecture a very unique role with a big community of researchers and contributors. Okay. Wait, let me. How could I clean? Here. Good. Well, computer architecture, I have to be honest with you. At the very beginning, I think before 1980s of the real computer architecture come in, very beginning computer architecture is only the instruction set architecture or ISA. That includes the registers, memory addressing modes, operands, opcode, control flow instructions, and instruction decoding. Okay. But clearly today's computer architecture only put this as maybe a third of the total contents of computer architecture, because computer architecture now targets a lot more contents. For instance, we also target the specific requirement of cost, power, and availability, as well as the macro architecture, such as the reservation station, 5-stage pipeline, or cache coherence protocols, and et cetera, right? So there's so many things beyond just the single-threaded. So those are like a modern computer architecture. Even in the emerging computer architecture, we have like virtual machine, we have MapReduce. So for those of you who know MapReduce or Hadoop, those are the new computer architectures we design and being focused upon, right? On the right side, we have this computer architecture of the 5-stage pipeline, basically, okay? Let's see how it works. So first part of the purple, you see that? So this is the instruction fetch, F. Okay. And then we have the instruction decoding, right? So basically, you fetch the instruction, and then how do you understand those instructions, right? Like it's an addition, or it's a modification, etc. And then they put those kind of instructions into dispatch queue, like macro operation buffer, or register alias table, and then or reorder buffer, so that they can be dispatched for what? For execution, right? This is the execution part. So the instruction decoding. Well, the execution part is here, sorry. And then the green part is the memory access, like a memory loader. You see memory loader and memory storer, right? Well, for the execution, you have the ALU for shuffle or for modification, for addition, branching, etc., etc. And then once you finish, you probably can do read back to the register for later, next execution, right? So this is the 5-stage pipeline. A very rough idea, right? Later on, we're going to definitely make sure you understand everything, right? Where can I go back? Oh, okay, here we go. So I don't know whether you guys heard about Moore's law. Okay, it's from Gordon Moore. So Gordon Moore is was the CEO of Intel. Okay, in 1965, Gordon Moore said that the number of transistors that is integrated in an integrated circuit will double every year. So basically, we have N transistor in 1965. Then we're going to have 2N 1964, 4N 1967, right, etc. Clearly, it's impossible. I mean, according to our current sense, but that is the reflection of how ambitious the semiconductor the companies they had, how famous they are. They are very ambitious. They're like the golden area of computer at that moment. Well, right now it's more like machine learning, software computing, or social media, those kind of companies, right? Well, later, Gordon figured out that we cannot surface from like a double, right? So when you go to 2 to n, it absolutely goes to like a infinite large of numbers, which you cannot definitely pack so many transistors in, due to either the end of Denote scaling or the limit of the atom limit, size, right? You cannot, for example, the atom size is the limit, so you cannot pack so many atoms in that specific integrated circuit. So later, at 1975, Gordon figured out that maybe we have to every 2 years double. This actually lasts for 50 years, which is a very long period of time. And this is very powerful. Why? Because think about it. If you can pack so many more and more transistors in the CPU, that essentially means the communication or the distance between different gates are reducing. And then the processing power is also improving, right? You have more and more gates or transistors. That means you are doubling your processing power. So when you have so many increments, then your performance will also sort of double every year. That's very powerful because that means you don't have to change any program. You only have to purchase a new CPU, then you have a better performance. This is very attractive. I mean, a sad talk. That's why when I was young, I heard those kind of advertisement like dong, 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 right? Every day in my television. Okay. Well, this sort of gave us the overall impression about the single processor performance from 1975 or 1978 towards 2018. This is 40 years, right? So, well, Moore's law starts from like 10 years earlier. So we can see we can partition the impact of different technologies to the performance gain into 5 different segments. From 1978 to 1985, 86, we see it's the purely we're packing more transistors in the CPU that matters. This gives us performance like almost double every 4 years. So you always gain performance without changing anything. Okay, that's actually very powerful. And then after 1986, we saw the performance getting even better. At this time, we do enjoy the technology advancement, while at the same time, we have the advanced architecture organization. That means not only packing more transistors in the CPU matters, excuse me, but also how do we pack them? Okay. How many goes to register? How many resources goes to cache? How do we put in different ALUs or reservation station or branch prediction? Essentially, how the 5-stage pipeline, register, opcode, operands, cache coherence, everything of computer architecture that matters. This actually tells us that it's not only technology advancement of the 1978 to 1986, but plus the advanced architecture organization, they together make the performance gain double, right? From 25% per year to 52% per year. It's actually more than double. Okay. Well, then we have the end of denied scaling. What is denied scaling? It actually means that for the same area of circuits or integrated circuits, the power consumption is constant, no matter how many transistors you pack in. That's actually very powerful and very useful, right? So that means you put one, it's like you have this large area, you put one circuit in, you consume 1 watt. Well, you put, as long as you can put like 1 million circuits in, it's also 1 watt. Well, you can say this is almost impossible because the area does not really, it has some relationship with the power consumption, but it's not exactly the constant. Well, end of denied scaling tells us that we cannot put so many transistors in the same given area, which means, in other words, right? So we have to give more power, okay? So let's say in the same area, you have 1 transistor, probably is the 1 watt. Let's give, I'm just making up things, okay? If you have 1 million, it's probably still 1.5 watts, but if it goes to 1 billion, it might go to 100 watts or more, okay? So that essentially leads to the multi-core, okay? when it goes to multi-core, then MDAS law is very important. We're going to also discuss very thoroughly about MDAS law. Basically, it means when you have a program, what's the portion of the program that can be parallelizable? It determines the speed up of moving to multi-core. Okay. So in other words, it means it does not matter how many cores you have. Well, how many cores you have matters, but the other half of the equation is how large of your program can be parallelized and enjoy these many cores, right? And then MDAS law ends. Then we have the ends of Moore's law. So basically, we cannot pack more transistors in a single core. So we have to only grow many cores, many cores. So that and gets us to like a GPU or Xeon Phi or recently Tensor processor or TPU or graph core, those kind of new technologies. So putting all of them together, this tells us the technology advancement is important and the computer architecture, right? So this also motivates us to the second lecture we're going to discuss later on. I think is that parallelism taxonomy, okay?